Anyway, Iain, welcome.
Right. Okay. I'm Iain Young, for those that don't know me, G7III. This talk is going to be more about measuring the Doppler on the lower beacon on the spacecraft more than ranging. But that would be the next step. But that's for a number of reasons that will become clear. So first of all, QO-100. As we know, it's geostationary, which should mean it doesn't move, right? Well, that's not quite right. The moon, the sun do exert gravitational forces on it, as do other things, and they make it do a figure of 8 around its orbital slot. So the question came, can we measure the Doppler effect, or observe the round trip time increasing and decreasing? So, this presentation, it's gone slightly wrong, was actually meant to include a measurement of the beacon frequency over time to show Doppler. It was also meant to include measurement of the round trip time for a pulse per second sent through the transponder every X minutes. Didn't quite turn out like that. It could easily have been called failing to show Doppler while measuring the spacecraft beacon, or failing to measure a pulse per second through the transponder. Now, I must stop here because this was correct as of Thursday night, and in fact as of Friday morning, 0030 hours, when I finished the bulk of it. Having had a conversation with Akim and Wouter last night at approximately 23:30 hours, this is now out of date. So, what I'm going to do is go through the rest of the presentation as I intended, but actually what I thought was a failure was actually what I should have expected to see, which is interesting, but we'll go through that when we come to it. So, the first problem when measuring the beacon. Most of my stations are GPS locked. There's one piece that isn't, the LMB. It means that the beacon appears to drift and wobble, theoretically at least, making Doppler measurements impossible. However, there is a solution to this. I can generate a local 10 gig beacon on the ground that I can receive through my wobbly LMB. I can measure its frequency. I know what frequency it should be on, and therefore I can calculate the offset, knowing how far off the LMB is. I can then measure the lower spacecraft beacon and calibrate its true transmitted frequency, or rather its true received frequency, I should say, rather than where the LMB said it was. So, the next thing I'm going to talk about is how I actually measure the frequency of any particular beacon. Yeah, I'll come onto more details of the whole solution in a minute. But how do we actually measure it? I actually sample 500 kilohertz. I then pass that through a 10 kilohertz low pass filter centered on the true frequency of the beacon. I pass it through an FFT of 10,000 bins and then measure the loudest bin. The more awake ones of you will notice the relationship between 10k bins and 10 kilohertz. It gives me 1 hertz resolution. And I can measure the loudest bin, i.e. who's got the strongest signal, quite easily because GNU Radio's got a block for it, the log power block, so it's easy to code. Now, that gives me a bin number, but with a bit of maths, it actually gives me the received frequency of my beacon. And so, therefore, if I know where my ground beacon is, I can apply an offset to another LPF to measure the frequency of the spacecraft beacon. I'd set my ground beacon 10 kilohertz below where the spacecraft beacon was. So, what have we actually got to do? We need to measure the received frequency of the ground beacon, and we need to measure the received frequency of the lower spacecraft beacon. We then do some maths. It ends up in about 12 columns in a comma separated file format. those columns were either a constant, i.e., for example, the ground beacon transmit frequency, blasted clippy. They were either measured, i.e. they were actually the frequency measured or actually received, or they were calculated from other columns. Those three colours, black, red and blue, by the way, you will see as we go through the presentation, and I list each of the columns. So that makes it easy to tell whether a column is actually measured or calculated or just plain constant. So, what spreadsheet columns do I have? First column is just the number of seconds since 1970, so it's a timestamp. The second column is just the my ground beacon transmit frequency. Again, it's a constant, 10.489.540 if memory serves. The third column was the measured ground beacon frequency. But by subtracting one from the other, we get the LNB drift. So column D is effectively column B minus column C. And that tells me my LNB drift at that moment in time. So the next set of columns are actually quite similar. Column E is the nominal spacecraft beacon frequency, 10.489.550. F is what I measured it at. G is column F minus column E. It's just the difference between the nominal and measured. But unlike the ground beacon, it also includes things like Doppler, atmospherics, any spacecraft artifacts, and anything else that I can't measure in the system. So while useful, not entirely useful. So, but we already know the LNB drift. It's in column D, for that second anyway. And the measured frequency of the spacecraft beacon, G. So we can remove this from the equation, yeah? So effectively, column H contains, and it's in Hertz, yeah, contains Doppler, anything caused by atmospherics, any spacecraft artifacts, and anything else unmeasurable. This is useful. Now this is where things started to go a little bit awry. We can, in theory, calculate the Doppler for the spacecraft at any given time. So I added column I, which is the Doppler at the time specified in column A from predict. It should, in theory, permit us to remove the Doppler producing column J, and I did do this. It then contains, column J will then contain only atmospherics, spacecraft artifacts, and other unmeasurables. Now, then, by reversing the equation, at least in theory, we should get the true Doppler, because we now take column H and remove column J from it. It should give us the true Doppler, without any of the other artifacts that I mentioned. Well, as I alluded to, I wrote the code to do it. It's really just a bit of subtraction. However, I actually removed the Doppler and kept calculating the residuals. But then I removed the residual instead. But the true Doppler, what I call column J, was always a perfect match for the calculated Doppler. That was a bit suspicious to me. So I thought, well, all right, let's push my predict server forward in the future. Because with predict, you don't tell it what time, you just ask it what the Doppler is now. And so I tried that, but I still got a perfect match. I can actually only suspect that I simply didn't have enough precision in either the measurements or the calculations. So that was the first real negative part. So with that in mind, because it's not, great, it's not quite what I wanted, I still decided to go ahead and plot column H, which contains the Doppler, atmospherics, spacecraft artifacts, and unmeasurables. Yeah. So this is what you're going to see next. Is not not true Doppler. All of this other stuff is in there as well. So this is what I got. Now, at first look, that actually looks quite a good graph, and kind of what I expected. And then I looked closer at the x-axis and realized it was over 2 days, rather than 1. Now you can see, roughly speaking, two cycles there. I was expecting to see 2 cycles in a 24-hour period, so 2 entire sine waves in a 24-hour period, not 1. But after a late night conversation on Friday night, it appears that that is actually correct for the frequency. Yes, there's a little bit of noise at the top. Yes, on the second one, there seems to be some noise on the right-hand side. What caused that, I don't know. Could be anything, to be honest. I let it run. These figures, by the way, or what you're seeing there, is I ran every 30 minutes, I took 10 minutes worth of data once a second. So 600 seconds worth of data. I did originally have the code running 24/7, supposedly, but it would get to 2.5 hours and just hang for some reason. But I thought, since what I'm actually looking at and knowing roughly what the spread should be, I can get away with just taking samples. The other thing that I did have to do was take out the outliers and then average it. The reason I had to take the outliers out is that the CW beacon, of course, is not a constant carrier. And so if I caught if one of the seconds caught when there was no carrier, looking at the FFT, there's still a loudest bin, so that it would still, even if it's just noise. So that had to be removed. It was very obvious which ones needed to be removed. They were just, no, the other end entirely. So, what were we actually looking at? And this basically, this slide basically covers what I've just said. Yeah. Now, I was going to ask if anybody had any ideas, but it appears that it's actually correct. So, no need. So, that was the measure the beacon frequency experiment. As to the PPS experiment, well, that was another issue. My uplink's fine. It was GPS locked and it was checked via Goonhilly. But currently I have an issue with my uplink desensing my downlink. I actually think it's probably just the fact that the two SDRs are very close together. They're actually in the same rack, and they share a MIMO cable between them. I suspect it might be getting in there. Unfortunately, they need the MIMO cable because while they both have Ethernet connections, one of them, the Ethernet connection doesn't work. But the MIMO cable acts as an Ethernet connection, so I can still talk to it. So that one is still to be carried out, but I am hopeful of resolving it, and I've just acquired a hack RF, which can take a clock input, so I can sync it to the same GPS. So maybe this time next year. So, summary of the problems encountered. Well, the NLB drift was fixed. The potential precision issue is still there that I got. 24-hour cycles versus 12-hour. I think that's probably been explained now. And the PPS uplink issue. So, now bear in mind this slide was written before last night. Was it a total loss? No. I'm still able to measure the beacon frequency. And I can see a periodic increase and decrease in that frequency. I found something that I wasn't expecting, which is always good in science, in my view. And the initial part of the experiment gives me a method to remove the LNB drift, which then give me a stable lower and upper beacon to feed the CW and PSK-400 decoders. I had tried some earlier code in GNU Radio for that, but it wasn't working very well, mainly because, again, the CW nature of the beacon. And I think, yeah, so the next steps that I'm planning to do, well, I'll skip the first one. I've got to fix the downlink descent issue. And yes, I'll add outputs to the same flow graph for upper and lower beacons to feed the decoders appropriately. So yes, that's about it from me. Thank you for listening. I know it was a bit more sciencey than some of the others we've had, and quite dry, but at least I was actually able to measure the frequency and actually see something. Yeah, but yeah.
Give you a slow hands up now.
Behave yourself, or I'll get involved next year. Any questions? Yeah, I knew he would.
Yeah, thanks, Ian. It was an interesting presentation. But a minor question. If you've got a 10 gig beacon, a ground beacon,
Yes.
why were you not checking the Doppler on that instead of from the spacecraft beacon? Because that would be a constant signal, not a CW.
There would be no Doppler on the ground beacon because it was 3 foot from the LNB.
No, that's not what I meant, sorry. You're using the ground beacon to check your LNB drift,
Yep.
but is the ground beacon, I've answered my own question, it's on a 10 gig, not a 2.4, so it can't go
Correct.
through the bent pipe. I'll shut up and get me box.
Thank you.
Thank you, Ian. Very interesting. So my question is actually kind of related to that.
Yeah.
Only I'll finish the question.
Go on.
So you've got a 10 gig ground beacon.
Yep.
You've got a 10 gig beacon from the satellite.
Yep.
But you've got a dish which is pointing at the satellite.
Yes.
So you must have 2 receivers. So
Nope.
your receivers are both synchronized to
No.
the...
One. Well, I do actually, but no. I have one receiver that receives 500 kilohertz worth of bandwidth at once.
Okay.
Yeah. None of this 2.5 kc SSB stuff. 500 kcs, half a meg.
Sure.
Centered roughly on in a position where the lower band, the lower transponder turns up, and slightly further left of it to account for any LNB drift. Yep. And so I'm receiving from 10.489.250-ish up to 750-ish.
Mm-hmm.
The spacecraft beacon is at 550.
Mm-hmm.
My beacon is at 540.
Okay.
So they both come into the LNB.
The ground beacon is running white box.
Yeah.
Yeah. Okay. Got it.
Hidden behind the dish, down a length of RG58 into a dummy load, hidden inside a metal pipe, and it's still a little bit too strong for my liking.
Okay. Got it. Thank you very much.
It wasn't 10 meters though.
Any more questions?
Akim has one.
Sorry.
Maybe not so much a question, but a comment. Just 3 weeks ago, Michael Fletcher, OH2 AUE, has made a YouTube video or tweet, and it says, "Some insist Doppler is not an issue with geostationary satellites." Not necessarily true. And there's a video, and I mean you can watch it later if you go on YouTube. But actually, what he did is apparently he locked his LNB to an oven reference, whatever, and had some down converters and an IC402, and had the LNB on his dashboard on his car, driving around, and therefore measuring the Doppler of his car relative to the satellite. You don't. No. You don't need any dish.
No.
If for the CW beacon alone, the LNB is just fine.
Oh, I suppose, actually, given that the beacon comes from the ground, doesn't it, rather from the satellite? So
It
you
is
get the
actually,
Doppler twice, as it were.
yeah, the observed Doppler, which is also was another clue as to why I think that the precision isn't right in the later calculations with taking Doppler out, because the observed Doppler is actually the S-band uplink Doppler plus the 10 gig downlink Doppler plus whatever else. But predict, I know I had it set on 10 gig because I did the calculation for 10 gig. I need to add the S-band uplink.
Any other questions?
I did hear.
John G7ACD. This is going to be a movable feast, though, because probably monthly, every 6 weeks, they'll do a north-south manoeuvre to zero out this Doppler.
Yeah, so it should,
So you've got,
depending on when I do it and when they do it.
Yeah.
Yeah.
You could find that there's no Doppler the day you look, because that's when they've completed the manoeuvre.
Well, we will know what they've been playing out there.
And if you get them doing the manoeuvre itself, then you've got very big figures.
Well, but I think that's actually a good thing, right? I mean,
You two are trying to give me exercise, aren't you?
well, we have some 20 minutes left, Barry. Well, I think that's a good thing. I mean, look at this beautiful plot, right? You can easily fit something through it and predict for the next couple of days. And whenever you have a slightest deviation from this, you can infer basically that the ground station has done some station keeping maneuvers, right? And if you're really clever, you can actually tell how much of station keeping they have done in what direction. I mean, Wouter is laughing. Like we had this discussion yesterday in the evening, right? And I mean, isn't it wonderful that we can measure 10 gigahertz frequencies down to the level of tens of hertz? I mean, that's 10 to the minus 9.
That's down, actually.
Isn't amateur radio brilliant?
Thanks very much. Am I coming running back up the floor? No. Excellent. Okay. In that case, if there are no more questions, can we say thank you again to Iain for excellent piece of research?